Hello everyone, this is Dr. Young, and in this video I'm going to introduce you to solutions and start talking about what solubility is and some of those solubility trends. So let's take a look. So first, some definition stuff. When we're talking about aqueous solutions, when you hear the word aqueous, what we're always talking about is water. So aqueous solutions means a water solution. You can have solutions in other solvents, right? Like you guys may have seen rubbing alcohol or gasoline or any other nail polish. There are other solvents. In organic chemistry, there's a whole bunch of solvents we use. But in these introductory level classes, we're going to be talking about water a lot since it's a very, very, very common solvent. So we're going to look at aqueous solutions. So anything you see that has the word aqueous in it is talking about water. And you might see the word aqueous abbreviated as AQ, just as a side note. So AQ. And now a solution, the definition of a solution here is just something that it's a type of mixture, and it's just a clear homogeneous mixture of at least two different things. And by clear, I mean just that you can see through it, right? So see through. I don't mean colorless. You can have something that is colorless and clear like water, but you can also have things that are like blue, but you can see through them, that are clear. So if you can see through it, then it's considered clear. If you can't see through it, then it has some undissolved particles in it. You have some sort of colloid or suspension or something like that. And then within this, right, we have two different words we need to define, right? So solutions are made up of two components. They're made up of the solvent, which is the thing that is present in the greater proportion. Usually for us, that's going to be water. And then the solvents, which are the things that are present in the lesser proportion or proportions. So that's the definition. It's not like the thing that dissolves and the thing that doesn't dissolve. It's just whatever is present in greater or lesser proportions. So let's take a look at something that we're familiar with, something like Kool-Aid here. If I look at Kool-Aid or any, Country Time lemonade or whatever, if you make Kool-Aid, right, we're going to have water. You mix water together, and then we all know that Kool-Aid has a bunch of sugar in it, and it's got a bunch of dyes and maybe flavors and some salt and all kinds of things like that. But if I want to know what the solvent or solutes are, right, water's definitely going to be the solvent because that's the thing that's present in the greatest proportion. You have more water than anything else. And then we would say that all of these other things then we would consider solutes. So since all of these are present in proportions smaller than water, these would all be our solutes. So we'd have a whole bunch of solutes, only one solvent. If I take a look at something like rubbing alcohol, 70% isopropyl alcohol or isopropanol, when it's saying it's 70%, that means that the other 30% basically is just water. So in this case, the other 30% is water. And again, given that the solvent is the thing that is present in the greater proportion, that means that in this case, it's my isopropyl alcohol that is my solute, because apparently it's 70% that. And my water in this case is not the solvent, it's the solute, because it's present in the lesser proportion. So don't always think that water is necessarily the solvent. If water is the thing that's present in a smaller amount, then it's a solute also. And let's look at something like blood plasma. A lot of my students go on to join the allied health professions. So let's talk about blood plasma. Blood plasma is, roughly 95% water. And then roughly 6% things like proteins, different salts, stuff like that. And these numbers vary, a little bit over the day, how much water you've been drinking, person to person. But blood plasma definitely is a solution that contains water as the solvent. So much more water than anything else. And these proteins and salts that are dissolved in your blood plasma are the solutes, all of those sodiums and bicarbonates and chlorides and things like that you'd find in there. And I put blood plasma, not the actual blood. We're assuming that you get rid of all those red blood cells. So again, the solvent is the thing that's present in the greater proportions. The solute is the thing that's there in the lesser proportion. Now, when we talk about solutions, something that we need to talk about is this idea of solubility. And solubility is just defined as the maximum number of grams of a substance that can dissolve in 100 milliliters of water. So if you take something, and so if you take something that we know is soluble, for example, right, that we know we can dissolve salt in water, for example here, salt water's solubility is 35.7 grams per 100 milliliters. That means you can dissolve just shy of 36 grams if you had 100 milliliters of water. You have more water, you can dissolve more stuff. You have less water, you can dissolve less stuff. And so these solubilities of things that we are familiar with, right? We know we can dissolve salt in water. We know we can dissolve sugar in water. It has much higher solubility. Things like chalk. I put calcium carbonate here. This is chalk or limestone. We know that these are not as soluble in water. You put a piece of chalk in water and it's not going to go anywhere real quickly. Just very little of it's going to dissolve. Baking soda is actually not that water soluble, only 6.9 grams per 100 milliliters. And it's kind of funny to think about things like oxygen. Oxygen is really not that water soluble. Chemists would say it's insoluble, but clearly there is oxygen in water. Fish and all the other, aquatic life are real happy that there's some dissolved oxygen, but it's really not that much. You can just get like 8 milligrams in every 100 milliliters. It's not much at all. And then when you look at something like these fatty acids, right? Fatty acids, these are another code. This is part of, for example, a component of oils. Your oils or fats. Fatty acids are a component of those. And we can see it's really, 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 really low, right? And we know that oils are not soluble in water, for example. And so I don't expect you to memorize any of these names. I just want you to be able to interpret these. And so I don't expect you to memorize any of these values. But what I want you to be able to do is to interpret it. And so if I ask you something, like what's going to happen if I take 30 grams of sodium chloride and I dump it in 100 milliliters of water, what am I going to see? And since 30 grams is less than 35 grams, all of this is going to dissolve. It's going to be totally dissolved. It is not going to be saturated. So in this case, all dissolves. All that sodium chloride is going to dissolve, and it will not be saturated. It will not be saturated. Whereas if I took, say, for example, 50 grams of sodium chloride and tossed it in 100 milliliters of water, since 50 grams is over 35.7, that means that not all will dissolve. So, roughly 15 grams or so, about 15 grams will not dissolve. And so, yes, that 36-ish will dissolve, but about 15 grams will not dissolve. And so you'll see, right? Everyone's seen this before, where you try to dissolve sugar or salt in something, and you see it just sits there on the bottom. You just see a pile of undissolved things. That means that you're saturated, right? That means that you've hit saturation point where no more will dissolve, and therefore we are saturated. This would be a saturated solution. And a saturated solution just means that you can no longer dissolve any more of that solute. And so in this case, we would see, little piles of NaCl sitting here at the bottom. That didn't dissolve is the idea. So these solubilities tell us, at what point we reach the saturation, how much can you dissolve? Now the solubility of something can change. I didn't mention on the previous slide, but those are all solubilities at a certain temperature and pressure. Now if we take a look, I've got this graph, I got it from ChemLibreText at this website down here. If you look at this graph, this is a graph showing you on the y-axis here, right, the grams of solute per 100 milliliters of water. So that's solubility, right? That's how much you can get in that amount of water. And then we have temperature as the x. So as your temperature increases, we can see that there's a relationship between the solubility of that compound and the temperature of that solution. And you notice that some of these curves go up as you move to the right, and some of them move down as you move to the right. So we have upward slopes and downward slopes. If we take a look at something like sodium nitrate here, right, you'll notice that as you heat up the temperature, you also increase the solubility. Same thing with potassium iodide. As you increase the temperature, you increase the solubility. And same thing, in fact, for all of these things that have an upward trend with temperature, all of these things are solids. So these are all examples of solids. And so when you dissolve solids and liquids in water, when you have solid and liquid solutes, what we tend to see is that for most everything, as you increase the temperature, what we see is that you also increase the solubility. You also increase the solubility of that thing. And that's true for most solutes and liquids, most all of them. It's a very good trend. And you may have noticed this before. I don't know if you've ever made like iced tea or hot tea, but if you put like sugar in hot tea or coffee, it dissolves really, really well. You don't see it sitting on the bottom, right? But if you have iced tea, you have a much colder thing, right? That colder solution, if you decrease the temperature, you have a decreased solubility. And so when you try to put sugar in like iced tea, for example, oftentimes you're frustrated, right? Because it's just sitting in the very bottom of your glass and it's not quite dissolving. So an example of this might be, hot versus cold tea and sugar. So you might see examples of something like that, right? Hot and cold solutes. Another kind of physiological example would be gout. So I don't know if you've heard of the disease gout. The idea is that with gout, what happens is you form uric acid crystals. So uric acid crystals. Your body forms uric acid crystals, if I can spell crystals. Sorry. Your body forms too much uric acid and you can't quite get rid of it, and so you form these uric acid crystals. The problem is that when the uric acid crystals form, they're really, really painful, and so they often form in joints and places like that and cause people a lot of discomfort, a lot of pain. They can damage organs. It's a nasty disease. But it's a nasty disease because it's a solubility disease. The solubility of uric acid is 6 milligrams per 100 milliliters. That's the solubility of uric acid. And so your body fluids can't really dissolve all that much. It's pretty soluble, but not that soluble. And if you've ever known anyone who has gout, you may have noticed that they're much less comfortable, much higher pain, oftentimes at night. And that's usually because at night the environment gets cold. And when it gets cold, right, your limbs get kind of cold too, right? Your fingers get cold, your feet get cold. And when those parts of your body, when the temperature of the parts of your parts of body decrease, that also decreases the solubility of the gout. The solubility of the uric acid. And when those uric acid crystals start to form more, that's when you get these really painful sensations. And so people who have gout often like to stay relatively warm so that you increase the solubility of the uric acid and your crystals dissolve a little bit more. Now we can look at the same thing if you on this chart with the gas solutes. Right, all of these ones that have these downward trends, I'll do this in red here, all these downward trend ones, so like HCl, ammonia has a downward trend, SO2, sulfur dioxide has a downward trend, those are all gas solutes. And you'll notice with those, as you increase the temperature, it's the opposite, right? So as you increase the temperature, what we see is a decrease in solubility. You see a decrease in solubility because these molecules, right, for us, those are gas molecules at normal temperatures and pressures. Ammonia is a gas, HCl is a gas, sulfur dioxide is a gas at normal temperatures and pressures. And that's because they don't have very strong attractive forces. So as soon as you start heating up a solution that has them, they have such weak attractive forces that they just leave that solution. They just pop out. There's nothing holding them in there. And so you see this opposite relationship. As you increase the temperature, your solubility goes down. Now with pressure, honestly, with solid and liquid solutes, we basically see no effect. There's not that big of an effect of the solubility on solids or liquids when you change the pressure, so we don't really need to worry about it. But gases, you definitely see a big effect. You see a big effect, right? And so here's another table from a different website, again showing solubility on the Y, and now an increase in pressure as you move to the right. All of these are gases, right? Oxygen, carbon monoxide, nitrogen, helium, all gases. Solubility of all of them greatly increases as you increase the pressure, right? As you kind of push them, you can kind of push them into the solution. They'll stay in the solution. If you decrease the pressure, then they come out much more easily. And so one way to say this is that as you increase the pressure, you increase the solubility of a gas. Of a gas solute. I know it's kind of weird for us to think of gases being dissolved in solution, but a good example of that would just be like a carbonated beverage, right? right? So carbonated beverage, right? Whether it's, soda, whether it's those popular seltzer waters, bubble water, right? Seltzer water, all those sorts of things, right? All of those are just carbon dioxide dissolved, right? So CO2 dissolved in water. So you have carbon dioxide dissolved in water there. That's all we're talking about. This is also can be expressed in what's called Henry's law. I don't care too much that you like memorize the name of Henry's law, but in Henry's law, this C stands for concentration, and the K is some constant. That constant changes depending on the gas that you're talking about, and P is the pressure. P is the pressure at which is acting on that solution. And so basically it's just saying the same thing, which is that your concentration of that solute is directly proportional to the pressure that's on that solution. So you have a higher concentration of stuff at higher pressures is all that it's saying. So, and then we'll see that this will be really important for those of you who are going to go take anatomy and physiology. It's all about how we exchange gases, for example, in our lungs, oxygen and carbon dioxide and other gases are all dictated by Henry's law, right? Higher pressures, you can absorb more gases. This does have some other interesting consequences, for example. There we go. If we take a look at, here's just another example here. So if we take a look at like scuba divers, I don't know if any of you have ever scuba dived. I used to scuba dive. But the idea, right, so here's my little scuba man. We're going to talk about them diving deep down. And so the idea here is that when you're high up, right, this is relatively low pressure. So I'll put lower pressure. And as you dive, you have all the weight of the water on top of you. That's at a much higher pressure. And for those of you who are not too familiar with scuba, we don't have to get crazy into it, but right, you have a tank of air on your back, and there's a regulator that allows the pressure that enters your lung to be the same as the pressure of the water around you so that your lungs work. If you didn't have a regulator on there, there's no way you could make your lungs open up enough under the pressure of all of that water. And so you always breathe the air that is the same pressure as the water around you. So as you go down, you're also breathing high pressure air. If you're at a lower pressure right here, right up at the top, that means that we have relatively lower pressure, and that means there's a relatively low solubility. Relatively low solubility, excuse me, let me erase that. Relatively low solubility of gas, which means that there's not much gas dissolved in your blood, right? Whether it's all of the oxygen, largely nitrogen and stuff like that, right? You don't have that much solubility. There's very little gas in blood. I'll just put little gas in blood. Now, as you move to a higher pressure, right, that changes, right? Because now you've increased the pressure, which means now you've also increased the solubility of that gas. And that in turn means that you have much more gas in your blood. And that's generally not a problem. It's not usually not a problem for you to have higher amounts of dissolved gases in your blood. That's fine. At some point you can get nitrogen narcosis, but that's not what the issue is here. The issue comes along where if you're swimming along all of a sudden and then you see like a great big octopus or something like that that's freaking you out, the instinct, right, that you're not supposed to follow is that the instinct is to simply just dart to the top really, really fast. That is a problem. That is a huge problem. You don't want to do that. If you do that, what happens is if you ascend really, really quickly, all of a sudden you go back to where there's lower pressure, and that means again your pressure goes down, and so your solubility goes down, and that means that all of a sudden that all that dissolved gas in your blood needs to come out really quickly. And that is exactly what you do not want, because then what happens is that the gases bubble out of your blood. So gases bubble out of your blood. And that is a big issue. That's what we call the bends. Where the gases bubble out of your blood, you basically are like a soda can that's being opened for the first time, you know, where you see all those bubbles form. The gases bubble out of your blood, and that's what's called the bends, or decompression sickness. That's how you get the bends. Or decompression sickness. That's why divers are supposed to come up slowly. If they go really deep, they're supposed to have decompression stops, so that you avoid that. So you just take you take your time and you just breathe out all that gas as it slowly comes out of solution. The treatment for this, people fly you real low. They don't want to raise you up too high in the atmosphere, but fly you real low, usually to a compression chamber. So they put pressure back on you to dissolve those gases back into your body, and then slowly release pressure so that slowly the gases come back out of you, and then ideally you're fine. So this relationship between pressure and gas solubility is a very important one. Now, the last thing that we can look at, right, so solubility depends on the temperature and pressure, but we also want to look at solubility as it relates to different structures, different molecules. Ideally, what we want to be able to say is like, oh, this molecule is soluble, that one's not soluble, this one is soluble, that one's not soluble, but that's going to be in the next video. So hopefully in this video, you have a better idea of what a solution is, what the term solubility means, and some things that affect solubility. And in our next video, we're going to basically go through all these molecules and decide, are they soluble or not? How do we tell? So if you have any questions or comments, please put them down below. Thank you.